না, ওয়েট দেখাচ্ছি। দেখতে পাচ্ছ? এই যে অডিও। হুম হুম, একটা শেয়ার হচ্ছে আর একটা স্ক্রিন শেয়ার হচ্ছে আর কি। এটা ওকে। হুম হুম, বুঝছি।
Everyone can hear, I think, now.
Okay. So assuming that I am beginning, and I must tell you that I am aware that I am addressing a very broad class of very broad class of audience, and therefore therefore there is some compromise has been made. But having said that, I must tell you that my first love is mathematics, and I'm more excited about logic and set theory because of its great connection with mathematics and ability to prove real deep outstanding problems, conjectures and have been solved. So only for 4 or 5 minutes, I may not be accessible, I mean technically, to some people, particularly from computer science uh, or statistics. You have to know a bit of algebra. So otherwise, I have made it. I have made a lot of compromise and try to make the language compromise with the language in which I am speaking, so that it becomes accessible to all of you. So I'm going to introduce you to what is called mathematical logic, and try to convince you that this subject is intellectually stimulating, and you know, there's a lot of challenges, and so you have a lot of scope for creativity. It is useful to mathematics and computer science. I will try to show both, and so whether it is stimulating or not is for you to decide. And for computer science people, just my slides, probably next or next to next slide will be spent on mathematics. And after that, you will see that how computer science, in some sense, why in some sense, I strongly believe that computer science was born in the hand of, unless the work of Gödel had come, computer science may have taken a lot of time to come into the existence. This I will try to convince you. And so this is what I am saying, that I will first spend some time, very little time, to show its usefulness to mathematics. And I will state some results, and mathematics student will say, oh, it is like usual mathematics. It has nothing to do with logic or philosophy or set theory. And the results will immediately be attractive, and you will be surprised to learn that they can be best proved. In fact, some of the results have no logic-free proof even. Okay, so here is first theorem. Now let F be an algebraically closed field. Okay, so something like a field of complex numbers is one of the algebraically closed field, or field of algebraic numbers. That means the roots of polynomials over rational coefficients in one variable. They are called algebraic numbers. That forms the field. So take an algebraically closed field, and this is the notation for set of all polynomials with coefficients coming from the field F and in n variables x1, x2, xn. So take n many such polynomials. This n and this n, these two are same. Then if you take any n tuple from F and compute the value of f1 at that n tuple, f2 at that n tuple, and fn at that n tuple, then it will give you an n tuple of fn. So n many functions, polynomials, in n variables with coefficients over f gives you a function from n-fold Cartesian product of f to f. And the result is that if it is 1 to 1, it is onto. So for example, you can try that, take f to be complex numbers, which all of you are familiar with. Take n many polynomials in n variables with complex coefficient. Then you get a function from Cn to Cn. And if it is 1 to 1, then it will be onto. I will certainly, as you can see, it is dealing with one of the most fundamental objects in mathematics, namely polynomials. And it is just saying that if a function is 1 to 1, this polynomial function is 1 to 1, then it has to be onto. So this has nothing to do with logic, as it said. And this was one of the major result proved and appeared in Annals of Mathematics. And I'm just giving you a brief outline of the proof, that using logic, and that's where logic plays a fantastic role, that you have to, this is Z by ZP. This one is really field of integers modulo P, where P is a prime number. And so this forms a field. Any algebraic students will know that addition modulo P, multiplication modulo P makes it into a field. And then you take the algebraic closure, the smallest algebraically closed field containing that. And and so instead of proving for all algebraically closed fields, you have to prove only for algebraic closures of Fp for any prime P. This is where the logic comes. And so the problem has been reduced drastically. And here problem has become quite easy for algebraic students. All that they have to know that finitely generated subfields of these fields is also finite, are also finite. Okay, once you use that, this whole thing reduces to showing that a one-to-one map from a finite set to itself is onto. So it just comes as a, I mean, such a beautiful argument that once you go through a little bit of logic, you learn, you get a fantastic result, which now some mathematics proofs using purely mathematics are known, but there are used quite a bit of other machinery, either from analysis or from algebraic geometry. Now here is another instance. So this is, you see here there was this a square bracket, and here it is third bracket. And this is the notation for the set of all rational functions. Okay, that means polynomial by polynomial, with real coefficients and in n variable. And the result is, so not for all n tuples of real numbers, this may have a value. You know, a polynomial by polynomial, the denominator at some n tuple may be 0. But if you are given that there is no, this f does not take any negative value. To give an example, suppose you have squares of polynomials, or sum of finite squares of polynomials, or sum of finite squares of rational numbers, then it will never take the value negative. And Hilbert asked a question that, is the converse also true? That means any rational function in n variables with the real coefficient, if it takes, if it does not assume value negative, does it have to be a sum of x square? And the answer is yes. Okay. Then f is this, and and this is another fantastic application, early application, which you can prove quite easily using some logic. And this result, both the results, access theorem and this. So access theorem is very interesting in what is known as algebraic geometry. And here the coefficient was real, and conventional thing is you take algebraically closed field and do the geometry. And here it is real. So this is a
recording in
result
progress.
In real, what is called the real algebraic geometry. And I give you one more example. So you see, what is Diophantine number 3? All of you understand Diophantine equations. That means you have polynomials over integer coefficients, and you want only integer solutions, or polynomials over rational coefficients, and you want only rational solutions. And there are questions about them. And number 3 very quickly goes into geometry, because you look at the curve by those curve of the equations that you want to solve, or the and so it becomes a geometric problem. And currently a whole lot of work is going on using logic at the interface of Diophantine number 3, or what is called also that. I club them together, the two subjects. So here is a definition, and I will tell you the importance of it. So a field F is called a C sub I D field, where D and I are positive integers, if every homogeneous polynomials. So what are the homogeneous polynomials? Polynomials are, you know, sums of monomials, and they all should be of the same degree. So they are called homogeneous polynomials. And if you take a homogeneous polynomial, then 0, 0, 0 will always be a root. And that will be, suppose you take a homogeneous polynomial over integer coefficients of degree at least 1, then 0, 0, 0 will be definitely a trivial solution. And question is that, can I get a non-trivial solution, non-trivial integer solution? And this F, such a thing, so in general, instead of integers or rationals, you take a general field and you call a CID, call it a C sub I D field, where D and I are positives. Uh, if you take any polynomial with with total degree D, that means each monomial occurring in that is of degree D in more than DI variables, then it has a non-zero root. So they are trying to find out the solutions of Diophantine equations. And here it gives the existence of a non-trivial Diophantine equation, existence of non-trivial root of a homogeneous Diophantine equation. And these kind of lot of work are going on. And you can see that the three examples that I have given has nothing to do with logic. It is by all means, in the heart of mathematics. And the conjecture was the following. So here, you require a little bit of more knowledge of field theory. So field of p-adic real numbers, I'm not going to explain it. It is something like, you have field of real numbers. So corresponding to any prime p, you have a sort of norm or metric on the set of rational numbers. And then you look at the metric completion and you get what is called field of p-adic real numbers. And this is extremely important field for number theory, extremely important. So we denote it by QP. Q is that you start with a norm depending on P, a particular norm, a very specific norm, on the set of rational numbers. And then a norm, or I will say metric or distance function. And then do the metric completion. And what you get is becomes a field, and that is what is called the field of p-adic real numbers. And this plays an extremely important role that in number theory. And this one is the notation for FP. I have already told you, FP is the field of integers modulo prime p. And I have double third bracket. So these are all long series, starting from summation, let's say minus m to infinity ai xi. Okay, so there are terms of the type 1 by xi also, but only finitely many. So they are called Lorentz series expansion. So you look at all Lorentz series, formal Lorentz series, with the coefficients coming from the field of integers modulo p, and QP, they also have a p-adic expansion. Like for general real numbers, you have decimal expansion. There is some kind of corresponding expansion with the, like a Lorentz series expansion, with coefficients coming from FP again. And they two look very alike, and they have lots of algebraic properties in common. And it was known that this guy is a field, is a C2D field. That means if you take any polynomial, any homogeneous polynomial with coefficients coming from this field of degree D, total degree D, but at least D square plus 1 many variables, then it has a non-trivial root. So because these two are behaving very similarly, very famous algebraist Emil Artin conjectured that QP is also a C2D field. So this was an open question for quite some time. And this is not exactly true, but a very, very deep result using logic was proved, and it was shown as follows, that take any D, there is a D appearing here. So homogeneous polynomials of degree D. Take any D, then QP is a the field QP of p-adic real numbers is a C2D field for all but finitely many primes p. Emil Artin has conjectured that for all p, but no, some counterexamples were given for some p. But whatever d you take for all but finitely many primes p, they will be C2D field. And till now, this is a very, very deep result. This is a very, very deep result. How do I remove this? In any case, it does not matter. So this is a very, very deep result. And me and my wife have written a book, Model Theory, a basic course on Model Theory, which is completely devoted to giving the solution to this. So you can see that you can do highly non-trivial mathematics using using logic, and that is one of my this is how I am selling logic to mathematicians. After this, I'm no more mathematics. I come back to logic, and I hope from now onwards I will be accessible to everyone. So logic, logic is the my definition of logic is the science of reasoning. Okay, how do we reason? Okay, and we are always reasoning. Oh, since this is true, that is true, or oh no, because this is true, that cannot be true, and things like that. So nobody gets training in logic, but still everybody reasons, and they try to contradict each other through some arguments, and you are convinced that no. If you know, if you have assumed certain sentences to be true, then you cannot draw a conclusion, or you can draw a conclusion. And the thing is that, question is that, to start with, it is a philosophical question, that is there a science of reasoning? Okay, can we axiomatize reasoning, like any abstract mathematics, or are there certain basic rules on which each of these things can be justified, that what we are drawing conclusion from certain assumption is true or not? This is a day-to-day life problem. And earlier, this question has bothered, this is philosophy is as old as human civilization, I would say. You must have heard the name of Aristotle, Plato, and so on. So let me give you the examples. To explain this, I will give you some example, which is just example from day-to-day life, not from mathematics or computer science or anything. So one assumption is every lady has long hair. Second statement is Manmohan Singh has long hairs. Therefore, Manmohan Singh is a lady. In other words, if you assume these two, does this follow? Everybody will say, no, it does not follow. Okay? Now, it does not matter, that from these two assumptions, it does not follow that Manmohan Singh is a lady. It is not a fact that, it is not that, oh, this is false because it is not a fact. The question is that this statement does not follow from these two assumptions. Okay? And this kind of reasoning you do. And that you will all agree that we can't conclude. And let's turn the question a little bit more. Let's twist this question a bit more. And now assume that every person having long hair is a lady. Okay? The earlier thing was every lady has long hair. The earlier assumption was every lady has long hair. And now my assumption is, that assumption is changed and said that every person having long hair is a lady. Manmohan Singh has long hair. Therefore, Manmohan Singh is a lady. And now all of you will agree that yes, if these assumptions, from these assumptions, it follows that Manmohan Singh is a lady. Now, this is just showing that example of reasoning. And it is very curious that everybody will follow to what I am saying, that yes, from these two assumptions, A prime and B, it follows that Manmohan Singh is a lady. But if I change A prime to A, that every lady has long hair, then from A and B, it does not follow that Manmohan Singh is a lady. So how is it, I mean, can we put a basis of reasoning? Can we develop a science of reasoning to explain how do human beings reason? And one more, okay, I will come to that. This is part of my slide. So these examples show that there is a system to the way human beings reason. Can we explain this system? I mean, can we explain it scientifically? Can we put the scientific basis of the reasoning, the way reasoning is done? And this, I have already said that this is a very old kind of curiosity, and it is, this kind of research and thinking is going on for quite some time. Now, here, whether your assumptions are right or not is not important. What is important is that from your assumptions, you can conclude what you want to conclude or what you are concluding. That is the question. Okay? Manmohan Singh, by just saying that, oh, Manmohan Singh is not a lady, therefore I cannot conclude from A, B that Manmohan Singh is a lady, that is not the argument. Argument is that can we conclude from A and B that Manmohan Singh is a lady? Or we can't say that, oh, we cannot conclude from A prime and B that Manmohan Singh is a lady because he is not a lady. Truth or this of these statements does not matter. Only that whether these statements follow, the particular conclusion follow from our assumption or not. That is the question, and that is kind of the broad definition of reasoning. And this is what I am saying. We need only to consider the structure of the sentences involved, not their truth, meaning, or content. Okay, your assumptions may be absolutely rubbish. If you see from real life point of view, if you say that every person that has a long hair is a lady, obviously most of the Punjabi gentlemen, Sikh gentlemen, they have long hair and they are not lady. But that is not the point. Point is that you have assumed it. You are allowed to make any assumption, but from those assumptions, whether you can conclude. So, now I want to just explain, why in case one, I cannot say that C follows from A and B, but in case of example 2, I can say that yes, C follows from A prime and B. Therefore, I have to, what we go is do the following. Now we are coming a little bit closer to scientific thinking, thinking like a scientist. So what I do is that I introduce a variable X, and which will be a generic notation for an element of discourse. For example, in our example, elements of discourse were all human beings. So let X be any human being. That is how we start talking. Then let us introduce two one-ary relation symbol, L and H. If I write Lx, it means that X satisfies the relation L. And if I write Hx, which will mean that just this notation will convey that X satisfies the relation H. in our example, instead of saying that X is a lady, I will use the word LX. So now this can represent any sentence. Similarly, in our example, instead of saying that X has long hairs, I will put HX. So you can substitute any property of human being, any statement about general human being. You can replace that particular statement B by that. And we introduce Manmohan Singh or whatever human being. So a particular human being I am talking of. So these are called constant symbols. So I can introduce a M, which will represent a specific element of discourse, whatever it may be. For example, those who have done little bit of algebra, when you say group, you will start with, a group consists of a group identity E. When you give the example E, example of a group, then E is specified. Otherwise, a particular element with certain property you are specifying. So here also, when you are talking of some particular individual or particular element of your your element of discourse, we introduce a constant symbol. Using these, now let us see how does A prime, B, and C are replaced. What is the general structure of the sentence? So A means every lady has long hair. Okay? And I'm making devoid of any kind of meanings of this. I have symbolically represented this. So I'm only interested in a sentence which has this structure, where L and H are unary relation symbol, and this is a logical symbol, implication. A prime was every human being having long hair is a lady, but that was distraction. No, I will now represent that in a generic way for all X. If X satisfies the relation H, then X satisfies the relation L. And this one is that M satisfies the relation H. That means Manmohan Singh has long hair. Now I have removed that, I have done HL. And LM is, M has long hair, or Manmohan Singh has long hair. Remove all those particular instinct.
That's a lady.
Oh, sorry, L was for lady, H was for hair. Excuse me. And these are the sentences. And now my question is that what we do, human being does, is that C does not follow if you assume A and B. And C follows if you assume A prime and B. Okay? Now there is now nobody can say, oh, Manmohan Singh is not a lady, and therefore I cannot conclude C from A and B. Those kind of things are not there. Or the assumption that everyone which has a long hair is a lady is not a correct statement. We are not interested in this. We are interested in the structure of sentences, and from such formally and precisely stated statement, how do we conclude some other statement? Okay, that is our question. And first I will tell you that how in day-to-day life, we will say so that C does not follow from A and B, and also so that C follows from A and B. Okay, so let us proceed. Now, set of discourse. There in my example, it was human being, but it did not be a human being. So you take any non-empty set M. X, the variable X represents a generic element of M. Okay? And then, corresponding to the relation L being a lady, you are only getting a unary relation symbol. So you fix a one-ary relation on M, which is nothing but fixing a subset of M. Similarly, having long hair is just a property. So you take any arbitrary interpretation of it, any arbitrary one-ary relation symbol of this. And corresponding to the constant symbol, you fix any element MM. And these are called interpretations of L, H, and M in M. And very soon you will see that people introduce the notation. They have a language. In our language, the alphabet is the special alphabets, apart from logical symbols. We have a two unary relation symbol and a constant symbol. And then an interpretation by an interpretation of this language with these three symbols in our our alphabet. What we get are called the interpretations of this language in M. From here, you will see the general definition. I will not be giving the general definition, but it can be very easily generalize this notion. You can think of a very broad notion of interpretation and very broad notion of languages. Okay, A is true means what? If someone is a lady, the hair is long. In that particular interpretation that I have taken. So that just means that LM is a subset of HM. If X belongs to LM, X belongs to HM. Satisfying unary relation just says that it belongs to that that subset which we have fixed for the relation. Similarly here, if A prime is true, will just mean if and only if HM is a subset of LM. Everyone which has long hair is a lady, if that is my interpretation that I give. And B is true in this interpretation just means that the interpretation of M, the particular individual that you have taken, satisfies the relation H. That means it belongs to HM. Similarly, C is true just means this. Now, to show that A and B implies C, what you have to do that you have to assume that suppose LM is M is an arbitrary non-empty set. Suppose LM is a subset of HM, and suppose a particular element belongs to HM. Does it imply that that element belongs to LM? And you can easily give example, okay, of subsets of M, an element of M, such that LM is a subset of HM, and you can interpret, you have interpreted M, which is in HM, but not in LM. You can always get a proper subset, proper superset HM of LM and 2. And that is how you argue that no. This shows that M sub M is not a lady. On the other hand, and this kind of arguments in mathematics parlance is called a counter example. So immediately you will give a counter example that this does not happen. Oh, look. And another term that will come is the model of a assumptions, model of a theory is that logicians call an interpretation which satisfies the hypothesis, which means the assumption, a model. So this one that I have described is a model of A and B. A and B, A says LM is a subset of HM, and MM is just an interpretation, arbitrary interpretation. And in that interpretation, in this way, if you give this kind of example, then you are seeing that A is satisfied, and there is a particular element, which satisfies H but does not satisfy L. So we have got a model of A and B which does not satisfy C. So, and this is precisely how mathematicians will give a counterexample and say that C does not follow from A and B. On the other hand, to show that C follows A prime and B, okay, you have to take all possible models. What people do is that take all possible models, and in that they argue all possible models of A prime and B, and they say that in any such model, C is true. And in our case, I was giving the example 1, HM is a subset of LM. Just say that everyone has a long hair is a lady. That means A prime is true in this interpretation. Okay? And B is true is just saying that MM belongs to HM. Okay? But anything that belongs to HM also belongs to LM, and therefore MM belongs to LM. And so it shows that in every model of A prime and B, C is true. That is precisely how mathematicians think. For example, if somebody wants to show that something is a theorem of group theory, they will take any group. That means they will take any model of group, a group theory, and there they will check that what they want to prove is true. If that happens, then you say it is a theorem of group theory. And for any other theory, that's precisely how mathematicians do. Or anybody does. Most of the people argue like that. They don't go through, meaning of what is logic and what is reasoning and such. There is an interpretation, there is a model, and if there exists a model which satisfies the hypothesis but does not satisfy the conclusion, you say that you cannot prove that from there. On the other hand, if there exists in every model which satisfies your assumptions or axioms, something is true, then you say that is a theorem of that. It follows from those assumptions, from the axioms. Now, keep it in mind, I have given a very simple day-to-day kind of example, and I can't think of an easier example than this to give. So the kind of argument that we do, this is called semantic, and it depends on the meanings, okay? And that is how any slightly, enlightened or educated human being, and certainly mathematicians argue. But the problem is that it does not give you the basis of reasoning, what are the axioms which are being followed. It is very, this is a very, very abstract proof. It does not throw any light of how do human beings reason. And what did we do? If you see some difficulty, just apparent difficulty, which is quite apparent, is that to prove C from A prime and B, we considered all possible models of A prime and B. That is huge. That is not even a set. That is a huge class of collection of objects. And in that, you are trying to prove that C holds. If you think of it, that obviously you didn't take all possible groups. You took any group which satisfied those axioms, any model of the assumptions. And in that you are arguing, and when you are arguing, you are certainly using some logic. Okay? You are not specifically looking at each and every model of the hypothesis, and there you are examining whether the conclusion is true or not. So even in these kind of arguments, there is a logic hidden, and we want to unearth that what is that logic, and that's all the logic is all about. Okay, so that's precisely what. Now, the example of statements that I have given you, there is one thing that I should say. I have used parentheses, but I'm not going into details of logic formally stated. I need not use parentheses or such. You will see that it is a finite sequence of symbols. It's nothing more than a finite sequence of symbols. And which each of the statements, that assumption that you are doing, has unambiguous syntactical structure. The unambiguous word is very important in logic, because if you use English or Bengali or Hindi or Tamil or whatever, sometimes you find that a sentence may mean, one sentence may mean many things. But here, the what is called a formal language, there the sentences have very, precise, unambiguous structure, syntactical structure. Okay, and so you would like that, no, instead of looking at this going in this highly abstract way, I would like to only concentrate on the syntactical structure, these finite objects, and from there try to conclude whatever I want to conclude, using certain principles of reasoning. And this is the goal that we are trying to achieve. In other words, we will state certain principles of reasoning, such that based on that, I'm going to about to define the notion of a proof, that anything has a proof if and only if it is true in all models. Such a result, such a thing we are looking for. This is obviously, you can see that it is it must have been an extremely challenging job. Was a challenging job. It is a philosophical question, because now I am asking what is reasoning. These are precisely these kind of questions that philosophers ask. Oh, sorry. But the research in this area, how do I go away from here? This is distracting me. This thing is distracting me. How do I go away from here? Now what happens is that once you answer this question, you will see, how did it go away?
Sir, I think you can just extend the screen you can just move on to the full screen mode. The second last icon from that.
This is what you said?
No, sir. Sir, you go to the icon.
What is the icon? Here?
Yeah. The second last icon from here.
This one?
Yeah.
आ गया.
I think it can be tracked then.
Oh, okay. But you see, this was a philosophical exercise, and common अरे बाबा ये philosopher है, इसके पास से भागो. But you will see that this question was answered very, very successfully, and it really brought in eventually the era of computers. Okay, so let me now proceed to give, what I'm saying, what is the principles of reasoning. So I'm trying to explain to you what I mean by that. That means I'm trying to state you the problem more precisely, so that you can understand. Still, it is somewhat vague, the question that I am asking. Okay, so for that, what I am saying, syntactical proofs are those which only depends on the syntax of your sentences that you are considering. Okay, exact way of formation of the sentences. Hmm. Hmm. So depending on syntactical structure of sentences, we shall give our proof using some logical laws. Something which we say, oh, logically it is so. And I will state some of these logical laws and some of the ways you infer some sentence from some other set of sentences. Okay? Now, the assumptions that we are making, this is non-logical action. This has got nothing to do with your logic. Like axioms of group theory, axioms of ring theory, or axioms of theory of numbers, piano arithmetic. They are specific to particular theory. Okay. For instance, now I am proceeding to give you examples of what are known as logical axioms. Now, whenever you reason, okay, don't be a intuitionistic, great logicians or such. Be a common human being. If you take any sentence, you say either that sentence has to be true or that sentence is false. You don't have anything in between. Okay. In other words, any sentence of this form, so this is my notation for negation, okay? And this is my notation for disjunction, or. So you fix a language, you take any sentence of that language. By language, I meant you fix the non-logical symbols, like L, H, M, and this that we were doing. You fix that and form sentences, and then A is an arbitrary sentence in that language, and then you say either A is true or A is false. This is the thing that we always do. In other words, in every interpretation, whatever may be the interpretation, in every interpretation, this sentence is true, is how you argue. So this I will call a logical axiom. So those sentences which are true in all interpretations of the language are called logical axioms. A popular word for it is that, and that may ring the bell to you, they are also called tautology. Okay? But the word tautology is reserved essentially for what is called propositional logic. Okay? But I hope I have conveyed to you that sentences which are true in all interpretation of the language is a bona fide candidate for a logical axiom. Another set of sentences, which is another such example, is this. If a property phi, so this denotes a property phi for some element of discourse X. And if you say that phi is true for every element, then you can also conclude that phi is true for any particular object. So if you look at a sentence like this, for all x, phi x implies phi t, where t is a constant symbol, or t, okay, t is some term or whatever you call it, but at the moment, don't be too fussy. T is a constant symbol like m. Then if you say that if something is, if the phi, a property phi holds for everything, it holds for every particular thing. This kind of reasoning you do. And in any interpretation, when you try to assume that a property holds for every element of that interpretation, that means corresponding M, corresponding a structure, it is true for a particular structure, obviously. So this is another example of a logical axiom which is true by the logic. So I believe I have given you some impression of what is a logical axiom. Axioms which are true in all interpretations. But imagine, you can think of thousands and thousands of such statements. okay, which are true in all models. So there are any number of, by the way, here you see, if you can see this statement, you will see that I have not said one particular sentence is a logical axiom. This is a scheme of logical axioms. Whatever may be whatever may be the unary predicate phi, whatever may be, if this happens, then this happens. Okay. Similarly, the earlier one is also not one axiom. There can be any number of sentences. So this is not one logical axiom. What we call is a logical axiom schema. It is a scheme of logical axiom. Now, one more thing I want to tell you, a trivial thing for computer scientists is that you can mechanically determine that whether a sentence is in this form or not. Okay? You can write down an algorithm, you can write down a computer program which will take any sentence as an input and will come with an answer yes, if it is of this form, or not any sentence here. I mean, which will take any sentence as an input and which will come answer yes, if it is of this form for some sentence A, and come out with answer no. So there is something mechanical about it also to determine whether something is a logical axiom or not. I will elaborate on it much better later. Okay. Similarly, here also these are logical axiom schema. Each one of them is a scheme of logical axioms. So sentences which are true in all interpretations are called logical axioms, or I should have said, are a bona fide candidate to be a logical axiom. Another thing is that we conclude one sentence from a group of sentences by the sheer logic. For instance, suppose you assume negation A or B, where A and B are sentences, and you also assume A or C. That means assume that negation A or B is true and negation A or C is true. Then you will conclude that one of B or C must be true. Okay? Because if you have assumed this, then take the sentence A. If this guy is true, then negation A is not true, and therefore B is true. So one of B or C is true. But if this guy is false, then A must be true, and therefore, then A must be false, and therefore C must be true. So one of B or C is true. So this is here, I am only using the structure of the sentence, and we are concluding this from these two assumptions. Okay? Again, you can see that you can kind of mechanically determine whether this is true or not, whether you can conclude this or not from certain finite number of statements of this form. I will elaborate on it later. That is where the magic of Gödel will come. And we call them cut rules. Another very, very famous rule is what is called modus ponens. If you assume that A is true and A implies B is true, then you conclude B is true. So this is another scheme of rules of inference. So deduction such that in every interpretation, whatever the hypothesis of the deduction are true. So generally we write infer B from A implies B and A. So that's why the word come here, rules of inference. Okay, and these are a schema of rules of inference. So I'm now explaining you that there are certain things which is inherent in our logic. And that is how we argue when we are trying to prove it. whatever maybe illusion has been given to you that you are checking something is true in all groups, actually you are not checking. You are using this kind of reasoning to arrive at the conclusion from your hypothesis of the theory. Okay? So fix a sentence, T of sentences in some language E. And this is what we call the axioms, and this is what we shall call a theory. A theory is nothing but a set of assumptions, a set of non-logical axioms. You are only talking of, oh, this is an axiom of group theory. They are not only one kind of axiom that you use while doing mathematics or while doing any kind of reasoning. You are also assuming something which is by virtue of the logic, by virtue of the laws of logic. That is why we call them non-logical axioms and logical axioms. And now, what is a proof in a theory T, a syntactical proof? It is a sequence of sentences, phi 1, phi 2, phi n. Okay? In the language of whatever language we are working with, where for each of phi I, either phi I is an axiom, logical or non-logical. A logical axiom is always true. A non-logical axiom is true because you have assumed them to be true. Okay? Or this phi I can be concluded from previous ones by using one of the logical rules of inference. Such a thing is called a proof. Okay? You could see that now I am using only my assumptions and certain rules of inference and certain logical axioms to define a proof. It is a finite tree element. And computer scientists deals only with finite objects. So we have this. And everybody will agree that yes, phi 1, first one, there is nothing before. So phi 1 has to be either a logical axiom or a non-logical axiom. Okay? And therefore, it will be true by assumption or true in your every model. Phi 2 is either a logical axiom or a non-logical axiom, or you have inferred from phi 1. And if you have proved that phi 1 is true, then phi 2 is true. So if you take a proof, then in each of the phi I is true in models of T. Okay? And this is what we are looking for. That can we set certain logical axioms and rules of inference so that a sentence is true in every model of the theory T, if and only if it is true, if and only if it has a proof like this. Okay? So now I have explained what we are looking for. And okay, and we call this finite sequence a proof of the last one. Okay, in fact, you cut it down, take any initial segment, you will still have a proof. Okay. And this is what I have already said, that it only depends on the structure of the axioms and certain rules of inference and certain logical axioms. Now, as I said, that there are infinitely many logical axioms, infinitely many logical rules of inference. So you have still not said that, you know, is there certain basic principles on which entire thing stands? That means other axioms for logical reasoning. So I'm coming to that. So first of all, having described it, let me give you a syntactical proof of C from A prime and B. Okay, you see, everything that has a long hair is a lady, but forget it. This sentence, this is a sentence about X, this one, Hx implies X, Lx. It is true for all X. Therefore, it is true for any particular H. This is one of logical axiom. And this is your assumption, A prime, that everyone who has a long hair is a lady. Forget about the meaning. This you have put as part of your axiom. Okay, you have made the assumption A prime. Now, if this is like phi x, then for all x phi x, think of A and think of this as B. You have A implies B is true and A is true. So apply your rule of inference mod exponents on these two, and you have concluded HM implies LM. So this is the first element of the sequence of the proof. This is the second element of the sequence of the proof. This is the third element of the sequence of proof. Now we have assumed B. That means HM is a non-logical axiom. So this is like A. This is like A implies B. And therefore, use mod exponents. And final thing is that M satisfies L. Okay? So this is the kind of thing we are looking for. And I hope I have explained you the, in a very broad way, that what is a proof. And now the real story begins, that, the real problem lies so far is that there are infinitely many non-logical, logical axioms. There are infinitely many rules of inference. So you don't expect it to be, in that sense, very useful. So how to make the question that, on what our basic reasoning stands, and that is where we are coming now. So let me see. Now, this is a little bit of what happens in mathematics. You assume you study either number theory or group theory or ring theory or ordered field or set theory. There are lots of theories. They each have their own language. For example, in group theory, you only have a group operation to start with and a group identity. In ring theory, you have only two operations, additive operation and multiplicative binary operation, two constant symbols, multiplicative identity and additive identity and multiplicative identity. If you are doing rings with identity, similarly ordered fields. Set theory has only one binary predicate symbol, X belongs to Y, and so on. So I have described you that by a language, these are examples of languages. And a general theorem of languages, I will tell you the meaning why first order language in a little while. So to study all these together and to put them on logical basis, I'm trying to unify. Our language may have a set of constant symbols. I have not said a non-empty set of constant symbols. I have only said a set of constant symbols. For each positive integer n, a set of n-ary function symbols. For each positive integer n, a set of n-ary relation symbols. And in our language, we also have equality symbols. So computer scientists are much more interested in what is called a predicate or propositional logic. In mathematics, we have a higher form of logic, which subsumes propositional logic also. So, to a particular thing, a theory that you are studying, whatever you have fixed, I gave the example some, these are called non-logical symbols. And then we use variables. we use logical connectives like this, negation, or, and this, that, so on. Huh. Incidentally, we use only finitely many this. And not only that, just negation, this, and only one quantifier is sufficient to express all first order sentences. By the way, first order means that quantification is only over elements of discourse, not over subsets of discourse. That is second order language. Okay? So that is first order language. So you are used to using these logical symbols. For example, I say that I can only take negation and or, and there exist. Then you will say, how do you, what is A implies B? A implies B, negation A or B. So, negation A or B. So we can dispense with this. Or we can say this is the abbreviation, A implies B is an abbreviation for A, negation A or B. And this is the abbreviation for A implies B and B implies A. But then what is A and B? A and B may be abbreviation for negation of negation A or negation B. It is not true that any one of A, B is false. Okay? So we can do with this. Similarly, if I assume only there exists, then what is for all x phi x? For all x phi x, if you see, it is not true. So negation, there exists some x, negation phi x, for which phi x is false. So I can dispense with this. So you can assume that in my logical symbols, I have only negation, or, and quantifiers. Usually you need to use parentheses, but that is only for unique readability, unambiguity. But in mathematical logic, we also fix a convention, very strong convention, so that we can dispense with parentheses. We don't have to use parentheses. And that is why a sentence is just a finite sequence of logical symbols and variables, a sequence of them, which we fix. We don't know how many variables we will need. We will need only finitely many variables for each sentence. But if you think of totality of sentences, we don't know how many variables we need, but a sequence of them will do. So we first fix them. We fix logical connectives, we fix logical quantifier, but only finitely many. Okay, so we are non-logical symbols, logical symbols. Okay, an interpretation, I have already told you that an interpretation consists of a non-empty set M. For each constant symbol in your language, you fix an element C sub M. For each n-ary function symbol, you fix a n-ary function on M, n-ary operation, that means a function from Mn to M. And for each n-ary predicate symbol P, you have a n-ary relation on P. That is called an interpretation. And equality is treated like equality, interpretation of equality, that two elements are same. Okay? And then a set of sentences, okay? In this language, we think of them as non-logical axioms, like group axioms, ring axioms, field axioms, and so on. And the models of that theory are precisely those interpretations in which all non-logical axioms are true. Okay? Now, semantically, we say phi does not follow from T if there is a model M of T in which phi is false. And semantically, we say phi follows from T and that is what is called a theorem in the parlance of mathematical logic, if your phi is true in all models of T. That is the first kind of example, proof of C from A implies B, or falsehood of, falsehood of C from A implies B, and falsehood of C from, and the truth of C follows from A prime and B was done. So this is the semantical notion. And again, logical axioms and this we have done. And similarly, we can define the proofs. Okay, as a finite sequence, phi 1, phi 2, phi n, where each phi I is either a logical axiom or a non-logical axiom, or can be inferred by this. Having done this, now I think the story comes. For the first time, you have seen the name of Gödel appear. What Gödel did is that, and that was his doctoral thesis, is that he gave a finite set of logical axioms schema, finite, and a finite set of rules of inference, such that if T is a set of sentences thought of a set of non-logical axioms, then any sentence phi is true in every models of T, if and only, both ways. Phi has a syntactical proof in T, using those finite set of logical axioms and finite set of rules of inference that Gödel gave. So he picked that up. In other words, he is now saying that these finite set of logical axioms and these finite set of rules of inferences, I mean, these are all schema, they are precisely the basis of all reasoning. Whatever you can reason out, you can reason out only using these rules of inferences and these logical axioms. A great achievement, and working in seclusion and proving this theorem. Okay. This was Gödel's first major work in logic, which drew the attention of logic to him with this, and this is what is called completeness theorem. And completeness means the set of logical axioms and finite set of logical axioms and finite set of rules of inference is the complete set, such that semantic and is a complete set, such that semantic and syntactical proof, notion of proof coincide. Now, a little earlier than this, a Polish logician, Emil Post, had proved the completeness theorem for a weaker form of logic called propositional logic. This is something of much more importance to computer scientists. I'm not saying it is not important for mathematical logic, because we do rely on this part also. And here is what I am saying. Completeness theorem is certainly a 20th century logic. Okay, you have hearing names from Aristotle to Plato to George Bull and so on and so forth. Essentially, I would say that they only succeeded in presenting things symbolically. Only. So, okay. So when I will be doing things, I will be working in. Is there any problem? No. Okay. Now, so Gödel was the first to give such a thing, but his thing was not very friendly to computer or computing point of view. So subsequently, many other deductive systems, that means another set of
think there is a connection issue. I think sir left the meeting because of connection issue. Need to inform him.
Sir, he's saying something. I think.
Host disabled participant screen sharing. Can you allow me, please?
Prabhat, please see. Please enable the sharing.
Sir, I have allowed you to share.
No. Not yet.
Can you check now?
Yeah. Sorry. What happened?
Maybe connection
Party-
issue from your end.
Oh. Don't have Zoom client installed. But I cannot.
Sir, I think you have to go to the PDF window which you were.
Okay. Just a second. Yeah. I cannot see the.
Here it says something.
No, I'm having problem. I mean, I don't know. This. Is it okay?
Yeah, it's okay.
Okay.
Yeah.
Now, so as I said that Godel's system was not very friendly from computing point of view. So many other deductive systems came, and I suppose at least last time when I was in touch with computer science, theoretical computer science, it was deductive sequent calculus, mainly based on mod exponents, was introduced. And here is the most important part, and which I am going to elaborate, which is where the Godel's immense contribution will come, that all deductive satisfy a crucial property. It can be mechanically decided. At the moment, that time it was totally unknown. What is an algorithm? What is this? What is a mechanical process? So the Godel was the first who said, what do we mean by mechanically deciding, or what do you mean by an algorithm? But for the time being, you assume that you can write down a program. You understand, you can write down an algorithm. If a sentence is a logical axiom or not, that means you can have an algorithm which will take any sentence of the language as input and will come out with answer, and will always stop, will come out with answer yes if it is a logical axiom, or come out with answer no if it is not a logical axiom. And same thing is true for this. If you feed in your hypothesis of the inference, on your conclusion of the inference, to your algorithm, there is such an algorithm, then it will come out with it will stop on all possible algorithms, and it will say that yes, you can infer what you want to infer from your assumptions. Okay. Now, assume that all our non-logical axioms is also such that there is an algorithm to determine if a sentence is a non-logical axiom or not. See, if you are given, you say, oh, this is my theory, these are my axioms. You are implying, I mean, that what is an axiom, what is not an axiom. But how do you make it mathematically precise? And I believe this is the time when Gödel, this was the moment when Gödel introduced the crucial notion of algorithm. And those who want to do just think of mathematically, what is called a recursive function or recursion theory. So a theory T whose set of non-logical axioms is decidable. In other words, you know whether there is an algorithm to determine whether the sentence is a non-logical axiom or not. We call them to be axiomatized theory. And once you have the axiomatized theory, then if you are fed with a finite sequence of sentences, then you can determine whether that is a proof or not. Okay? And so on and so forth. So this is where it came out of the great importance for the era of, ushering in the era of computer science. Okay? So if a theory is axiomatized, it can be mechanically determined if a finite set of sentences is a proof or not. So, what is an algorithm, what is a mechanical process, and so on. I assert that it was first born in the hand of Gödel. Of course, his goal was different. Still, computer was not in his mind. But that was the beginning. And from there, finally, the notion of Turing machine came. And now it has blossomed into, for computer scientists, it has become an extremely important, it made an extremely important contribution to computer science. So now let us see how did Gödel do it. So one of the questions that you will ask, we have to make algorithms where the possible input set can be anything. It may be a sentence of a language, it may be a graph, it may be something else. But how do you feed them into the computer? Okay? And the computers only take, you can visualize that you can only feed in, integers, positive integers in the form of binary expansion. So everything has to be somehow reduced to a number theoretic problem. And only then you can put in the input inside the machine and then feed in your program and it will work. And this is the process that, this is how Gödel taught everybody, how to turn every algorithmic problem into an algorithmic problem in number theory, involving numbers. Now, we know a prime decomposition theorem that every positive integer is a product of prime powers. Now we enumerate, you enumerate all the primes in an strictly increasing order. By the way, given n, you can determine whether some integer is the nth prime or not. Okay. So now given n1, n2, nk, a finite sequence of positive integers, you can represent this finite sequence into a single integer, p1, n1, ... pk, nk. Okay. So integers to finite sequence of integers turned into integers. And what is important about this coding is that given any positive integer n, you will ask whether it is of this form or not. Notice that these are integers of the form. If a prime number divides that integer, all primes before that divides. Okay? Because these are positive integers. Huh? So, given any positive integer n, we can decode it and algorithmically and to decide which sequence it is coding, if at all it is coding. So first thing it will determine whether it is suppose n, take an input n, 2 does not divide. You will say, this is not a code of any finite sequence. Program stops. If 2 divides, it will go to the next prime and then it will say whether that divides or not. Okay? And keep on doing that. Moment you see that there is a prime number which divides it, but before prime numbers before that, you find one of the prime numbers before that which does not divide, you say that it is not an integer of that power. And again, once you determine that it codes an integer, okay, you will see its form also. You can compute that it is in which form. What is the highest power of 2 that divides n? What is the highest power of 3 that divides n? So everything is, accessible to mechanization. What was that? So this is what I have already said. Now, as I said that, how do you put everything as an input? I will only I will only do this for as if my my inputs are from sentences of a language, and the restriction is that there are only finitely many non-logical symbols. Okay, so if there are only finitely many non-logical symbols, now what symbol you use for variables does not matter. X, Y, Z, or A, B, C, or K, K, G, or 2, 4, 6, whatever you want, or 1, 3, 5, whatever you want, you can use. They are just symbols. Symbols is at your liberty. So what Gödel did is that instead of using these kind of things, he represented nth variable by nth odd number, nth positive, nth odd number, 2n plus. Sorry, it is 3. So he represented by this. Now notice one thing, that if you are given a positive integer, you will find out mechanically whether it is of the form 2n plus 1 or not. If it is 1, then you know that that particular integer represents which variable. So that reverse process is also mechanical. You can decode. Then, as I told you, there are only finitely many logical symbols. Odd numbers are filled in. So you use first 3, maybe 2 represents negation, 4 represents or, 6 represents their exist. And then followed by, this is my assumption, finitely many non-logical axioms, by represent finitely many non-logical axioms, non-logical symbols, of any particular theory by the following consecutive positive even integers, 8, 10, 12, and so on. Okay? And you know that 2 represents, let us say, negation, 4 represents, let us say, or, 6 represents, let us say, there exists. And if you are using group theory, maybe 8 represents the group operation, dot, and 10 represents the group identity, and things like that. Since any sentence, say phi, is a finite sequence of symbols, they are represented by a finite sequence of positive integers. Because now these symbols that you are using to make sentences is a finite sequence of integers, okay, because symbols are replaced by integers, and so it is represented by n1, n2, nk, which again in turn, using prime powers, p1 to the power n1 dot 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 pk to the power nk, is represented by a number. So these syntactical objects, sentences, are also represented by integers. Okay? And then a proof is also a finite sequence of statements. But these are themselves represented by integers, say L1, L2, Lm. But then again, in turn, you represent them by a single integer. Okay? So thus we can see that any syntactical object, whether variables or non-logical symbols or a sentence or a proof, whatever, is all turned into integers. You can feed in, you can represent them by integers, and given the integer, you can decode back and you know that what it is coding. Okay? And therefore, whatever logical question you will ask will be a question about natural numbers. Okay? What we call decision problems or, computational problems. So this way, any of the questions concerning syntactical objects is turned into a question in number theory or question involving numbers. And so it is now amenable to be fed in, that the inputs are numbers, are positive integers, you can feed in. And this was a great idea, absolutely brilliant idea. And then, as I was indicating, if your theory has only finitely many non-logical symbols, so all algorithmic problem, which there is a finite, begins with a finite alphabet, and then you represent them by a finite sequence, and that is what you want to code. That is your input. But then it does not matter what you use in your alphabet. Use the integers as Gödel is doing, and that's precisely how you write down algorithms for graphs, algorithms for whatever you want, provided each input is a finite sequence of certain symbols you have represented. Okay, and so this is the question, that whether, like one question you can ask, whether a positive integer codes a proof or not. Okay, or if you have a pair of integers nm, whether n codes the proof of a sentence whose code is m. Okay, and things like that. Or you can say m is a theorem, which means that there exists n such that n codes a proof of the sentence whose code is m. So m is a theorem or not. That also you can express. So all these various kind of syntactical questions is turned into now a sentence in number theory. and you want to examine whether that sentence is true or not. And forget it. Huh? Now, what happens is that at the turn of the century, or particularly after George Cantor's absolutely abstract way of looking at mathematics through set theory, the doubts were raised. It was almost like a crisis in mathematics, that whether mathematics is standing on the firm logical foundation. And the greatest supporter of Gödel ever, David Hilbert, said, no. There is no problem. All that you have to do is that you can find a mechanical definition of proof, the one that we have described that Gödel found, and appropriate axioms. So that time, for example, for number 2, he said, so that given any first order sentence involving numbers, that theory can decide, you can decide whether that is a theorem based on those axioms or not. Such theories are called, that means complete set of axioms or not. And David Hilbert made this program and also started working on it. And many people started working in it, and they believed in it. They believed in the firm logical foundation of that. And there are thick books written, but I would say that the only word that was spoken was by Gödel. So Gödel proved some very, very surprising theorems. A theory T is called complete if for any sentence A of the theory, exactly one of A or negation A is a theorem. This is actually 2 sentences I am making. There is no sentence A such that both A and negation A are true. So that means the theory is consistent. And given any sentence A, you can decide either A is a theorem or A is not a theorem. A is false. A has a proof or A does not have a proof. Or negation A has a proof. That means A is false. So such theories are called complete. And Gödel said that for number theory, and therefore for mathematics, because at that time, whole thing was, as you state, that God built integers and rest was built by mankind. So number theory was supposed to be the foundation of mathematics. And he says that you can find a complete set of axioms like this. And you can define a notion of the proof. Okay, and now here are the findings of Gödel. If T is a complete theory with only finitely many non-logical symbols, this is needed for his arithmetization and axiomatized. That means there is an algorithm to decide whether a sentence belongs to T or not. Then there is an algorithm to determine if a positive integer n codes a theorem or not, provided T is complete. Okay? Which means that given any sentence A, it will decide whether, by the way, the complete means there is no inconsistency. So it will decide whether which one is the theorem. So first he showed that. And the assumption is provided the theory is complete. If a finite consistent theory, now this is where I have not made it precise because it will require some time, is stronger than a weak fragment of number theory. Now, if you don't think too abstractly, if you just think that you want to give axioms for numbers, then there are certain axioms that you have to assume, and then any extension of that, you can take the sentence like this. Then Gödel proves that there is no algorithm to determine if a positive integer n codes a theorem or not. Okay? I have said it first because this just says that the core subset of all theorems is not decidable. You cannot write down an algorithm to determine is not decidable means that whether an integer n belongs to that or not. And then as a consequence, you get a finite axiomatized consistent theory T stronger than a weak fragment of number theory is never complete. Okay? There is no hope of complete axiomatization of number theory. And this came as a great shock to entire mathematics world, that you can't do it. Okay? And how did he, this work, I'm only trying to show that how beautiful was the argument. Already I have given you a beautiful notion of coding, arithmetization. That is also called Gödel numbering. And now I am telling you another thing that was needed here. He used a great idea called representability. Okay, again, I will not be able to define it precisely, but I hope I shall be able to give you a good idea of what it means. By which he expects a significantly important set of natural number theoretic statements. Okay, statements involving numbers only. And by statements, I mean first order statements. As a first order statement in a formal language of number theory. Okay, so you are going back, you have a question in number theory and you are turning it into a statements about the formal language. Okay, symbolically, you can represent. This was a great work of Gödel, but what is the impact? I cannot elaborate more than this. Now you see what happens. Suppose you are doing number theory. Okay, so you start studying number theory in its natural language, usual way, 2, 3, 5, 7, 5 numbers, this, that. But you have already seen that I can express many number theoretic statements unambiguously as a sentence in a formal language for number theory. So to study it logically or to lay down the foundation of the number theory, you write down the axioms, but to write down the axioms automatically variables, this, that, so on. So you have an associated formal language and you start talking in formal language. So you had a natural language for number theory and now it goes to a formal language for number theory. Then a number theoretic problems was turned into a logical problem involving syntactical objects, because you have expressed the problem in natural language to a problem in formal language, but then formal language, which means that you have turned it into a logical problem involving syntactical objects. Haha. But now you do Gödel numbering, arithmetization. So express all your questions, as I said, to integers and this and that. You have turned this thing using Gödel numbering back to a sentence or a problem in the natural language of number theoretic problem. And then using representability, what he did is that he said that significantly important set of number theoretic statements, and those who know what are called recursive sets, can be turned back into a logical problem in formal language of number theory. So what is happening is that natural language, then formal language, then you do arithmetization, you go to a number theoretic problem, and again you come back to representability. And for representability is where he needs the assumption that the theory has to be a little stronger than a weak fragment of number theory. By the way, you can see it precisely in my book on a course on mathematical logic. And so a strange loop is constructed. And we are each time looping between formal language, syntactical problems, number theoretic problems, natural language, and so on. This is undoubtedly a work of, it's for you to decide. I find it, mesmerizing. And a book has been written, Gödel et Bach, whose name is Gödel et Bach, by Hofstadter, who compares the work of Gödel, particularly this loop business, with the painting of Escher and music of Bach. And I told you, I tell you that I have read this book. Unfortunately, I don't understand music, nor can I read musical notation. However, the paintings are very easy for laypersons like me to understand. And it's a absolutely precise comparison. I can see Escher's painting and Gödel's work. A great, they are just parallel. And this book was published in 1979 when I went to Princeton at the age of 26 years. And that was the worst place to go because it is the greatest, it is the greatest place for mathematics, absolutely no doubt. Very lonely. And then whom I am seeing moving around, underway, Hassler-Whitney, Langlands, Harishchandra, this, and this ordinary fellow who went from a basti of Calcutta straight to Princeton had a mental breakdown because of the loneliness and because of all the people who are going around, walking around, Milner, this, that. And so I went for a psychiatric consultation. And the doctor asked me, psychiatrist, "Oh, why are you in Princeton? What are you doing here?" So I said, "I'm a member of the Institute for Advanced Study." And his face cleared. He said, "Oh," he took out the book, Gödel et Bach, which was published in 1979. And he said that Gödel was my patient, okay? And told me a lot of stories about Gödel. And at least I take a pride that you see, I was treated by the same doctor who treated Gödel for psychiatric, I underwent a psychiatric treatment under the same doctor who treated Gödel. Okay, and I hope he did a good job, as you can see me now. I'm no longer mad. I don't think anybody. It's for you to decide whether whether the doctor did a good work or not. Okay, and this already I have said that Gödel painstakingly developed the theory of computation, which ultimately heralded the era of computers. So let me elaborate a bit on more. You see, there is a notion, there is something called algorithm, Euclid algorithm or this or that, but nobody knows what is the definition. Okay? So if you are looking for an algorithm, something if you find and your mind says, yeah, this is a mechanical process. But for something you are just not able to find, there is a possibility that there is no mechanical procedure. And that is the time when Gödel introduced the notion of algorithm. But this cannot be an abstract notion. notion given by any person. It already existed. You have to capture it. So it underwent lot of examination and discussion. Each person came out with their own notion of computation. You know, what is an algorithm? Like Church came out with what is called lambda calculus, and Post came out with some other notion, definition that no, this is more natural. Ultimately, when Turing came out with this notion of algorithm, what is called Turing machine, and all will see that precisely they are coming out to be the same notion, equivalent notion. Definition is different, but ultimately they define the same class of computable functions and such that the definition was accepted after Turing's work. And then, you know, soon after, digital computer came into the force. And I do believe that that Gödel should be credited that he was the first person who was responsible so that we are now living in the age of computers, whose benefit nobody can deny. And now comes the second incompleteness theorem. I will just say a few words. Gödel expects the mathematical statement, set theory is consistent. This is a statement about a theory. This is a thing about, let's say, syntactic. This is a question in your formal language. No, sorry, it is a question in meta language. Okay, it turned into a formal sentence, which we denote by con ZF. ZF is consistent, and showed that neither con. Oh, this I should have put capital. Neither con ZF nor negation con ZF has a proof in ZF. That means set theory cannot prove its own consistency. Okay. And this is popularly said that mathematics can't prove its own consistency. Better assume mathematics is consistent and proceed. At least nobody can show you that mathematics is not consistent. And this ranks among one of the deepest and one of the most surprising results ever proved in mathematics. It is known as Gödel's second incompleteness theorem. And whatever mathematics you are doing, you know, it is on the assumption that set theory is consistent. So they are all relatively consistent theorems. Oh my God. Okay. So because of disruption and such, okay. So that's where I end.
Thank you, sir. It was really a wonderful lecture. We learned a lot of things from you, and really
Recording stopped.
the beauty of Gödel's work is